Welcome everybody to our SEDNOL from today. We are very, very happy to have Liliane Maia visiting us. She's right now in Querétaro, working with Monica, and she has accepted our invitation. Thank you very much, Liliane Maia. Liliane is an expert on partial differential equations in variational theory, in functional analysis. And today she's going to speak us, she's coming from the Universidade de Brasilia, and she's going to speak us about a degenerate parabolic logistic equation. Thank you very much, and please go ahead.
Thanks, Alberto and Monica, for the invitation. It's a great pleasure for me to be back to Mexico and to get to know Juriquilla and be here working with Monica. It's been a very nice invitation. Thank you so much. I'm going to talk today about a parabolic problem, which I have been working for some years with a colleague from University of Rio de Janeiro, Federal de Rio de Janeiro, Juliana Fernandes, a young mathematician in Brazil. She concluded her PhD in Portugal some years ago and got a position at University Federal de Rio de Janeiro. And for some years we have been working, and I have been learning a lot about parabolic equations because this is not my specialty. So we realized that we could talk elliptic parabolic, and then I could learn some things. So what I'm going to talk today is about the second work that we have submitted recently on the Nehari manifold for a degenerate logistic equation. I cut the Nehari from the title so that I wouldn't people would avoid it. So let me see where we can go. So I start with this, I cannot read my thing well here. Okay, mathematical model that comes from population dynamics. So this is something that I enjoy, knowing where the problems come from. And the prototype of this equation I'm going to talk today is the one that links Malthus and Verhulst laws of population dynamics in a same region. So let me try to explain what it is. Okay, the kind of equation I'm working with Juliana is this. The derivative of u with respect to t is equal to this Laplacian of u plus lambda u plus b of x g of xu. This is a very general way of writing the equation. We are going to work with something not so general. On the border, you have u, the solution 0, and you have the initial condition u0 of x. So let me try to explain the conditions. The bounded domain is where this population lives. B of x for us is less than or equal to 0, which means when b is 0 in some region, which we are going to assume with positive measure, that's when we say that the equation degenerates and the population grows exponentially on this region. So this is called the good region, where food is abundant and there is no restriction for the growth of this population. And for beta less than 0, we have limitations for the population. So this is a semilinear parabolic equation and degenerate because b is equal to 0 in some positive Lebesgue region. This, in ecology, this kind of equation models the distribution of single species in just one species in omega. Lambda is the intrinsic growth rate of this population. So depending on if it's rabbits or butterflies, they have this intrinsic growth rate. B of x is the crowding effect of the population. And the B of x equals to 0 is called the favorable region. There is not going to be any restriction on the crowding effect. Dirichlet boundary condition says that the omega is fully surrounded by complete hostile regions. So the population cannot live on the boundary. It's like mountains with, I don't know, all kinds of disruption that people cannot live very close to the boundary. And then you start with a population distributed in this region with favorable regions and not, crowding effect, and then you try to let the flow in time and see how the population is going to distribute, die, or grow. So in ecology, it's a very interesting because it's a very real model. The heterogeneous environment says that the logistic equation, depending on the g of xu, for example, if it's u, and you have the omega minus the b of x less than 0, then we would have something like a very simple model where you have the power 2 for the, how can I say, the meeting of the species, okay? So this is the most simple problem model that people in ecology have used to study populations. The spatial Malthus equation is when you have, for example, no negative, no bees. So if you have no bees, if the omega minus is empty, the population grows exponentially because basically you have a linear problem with lambda u, you will find a solution with exponential growth. But the kind of region we are thinking is something like this. Then we have the big omega. Omega can be 0 in the outside and in the inside of this annulus, for example. And then you have this hostile environment, which is omega minus. In omega 0,1 and omega 0,2, the population grows exponentially, no problem to grow. But here is the hostile environment where the population competes for food or other things. So this was well described in this famous work of Lopes Gomes, 2005, and he really gives a beautiful review of this kind of problems. And in his work, he draws a picture of what would be the limiting profiles of solutions. For example, if lambda that we have in the equation, if this lambda is less than some omega 0, which he called the first eigenvalue of the problem where b is 0. So if lambda is less than omega 0, you have the 0 solution only. If lambda is between sigma 0 and sigma 1, no, I think sigma 1 is sigma 0 and sigma 1, which is the first eigenvalue of the whole omega, you have a solution like this. This would be a profile, okay? If you cross the first eigenvalue of the whole space and stays between the first and the second, this would be a profile for the region, okay? For this region, for example, okay? Here, because you have omega minus, omega 0, and omega minus plus. This is omega minus, is a section, okay? And then if you have lambda very big that crosses the eigenvalues with respect to these two different regions, the solution has this discontinuity, which means that you don't have a real classical positive solution for the problem, okay? So in some sense, he gave an idea on how the profiles would emerge and disappear, for example, depending on how big and how small this lambda is. So this lambda dictates, in some sense, what's going to happen with respect to the different regions that you have for omega. And we are going to see this in our problem too, in our solution too. Okay, If we study the problem, as the problem evolves to a stationary solution, the stationary solution is going to be an elliptic equation. So we had to go back to the elliptic equations and find out what has been done on this elliptic equation of this problem. So if you take minus Laplacian of u, lambda u, plus some b of x, which is negative or zero in our case, in a very general nonlinearity, there are many works, but the most famous and let's say, the foundations of these solutions for the elliptic problems comes from Ouyang, 92, Ouyang, and also Alama and Tarantello, 93. So these are the most classical discussions on this elliptic problem. Ouyang studied just a power here, b of x less or equal to 0, for example, in his first paper, and then in the second paper, he used the b of x that changed sign, and used sub and super solutions in bifurcation theory in order to find a positive solution for this problem, a bounded domain. Alama and Taratello also studied this problem in a bounded domain, but they took a very general nonlinearity, a general nonlinearity that has asymptotes at infinity and in zero. And also they generalized studying the b of x that changes sign. So for them, Alama and Tarantello, Gabriela Tarantello, from Rome, they studied, for example, a b of x that has positive region, negative region, and a zero region. Using linking structure, mountain paths, and other things, they were able to give some descriptions of ranges of lambda where you have a positive solution for this problem. Depending on where lambda is, you have one solution, positive solution, two positive solutions, and no solutions. So for b less or equal to 0, power nonlinearities were also studied using variational methods, linking theorem, by Delpino and Felmer in 95. So these are, in fact, our the background we have used in order to study the problem. There are many others, of course. After 92, this became very well studied because it has the appeal of an ecology problem. So still nowadays there are many different trials, for example, with different operators and everything. But the origin comes from here, at least in our opinion, in the methods we use. Okay, but all these studies are using just mountain paths, minimum, sub and super solution, bifurcation theory. Only in 2003, Brown and Zhang introduced the study of this problem with a power here, not a general nonlinearity, using the Nahari manifold. So for us, this was the beginning of our curiosity. Why? Because I have been working in the past years with Monica and many others, variational methods minimizing on the Nahari manifold. So when I saw this paper studying this, I said, maybe, Juliana, we can study the parabolic and see what information we take from the Nahari set and let's say complementary sets in order to say something about the parabolic evolution of this problem. Because in general, in order to study the evolution, the parabolic evolution, people also use the studies of Lopez Gomes and many Spanish and Italians and also American, many people, okay, that work with these parabolic equations. They use sub and super solutions, maximum principle, comparison principles, but we couldn't find anything using the Nahari manifold. But we had already worked in a previous paper, an extension of a method developed by Gazzola and let me say it here because it involves the parabolic now. Gazzola, okay, so I'm going to say it here because it's more appropriate, because the curiosity started to see how to face this problem using Nahari, because all other papers were using sub and super solutions and other methods. But a problem like this had been studied with just a power here by Gasol and Wet. And we had studied this problem with not a power, but with an asymptotically linear nonlinearity. So we said, maybe going back to Nehari now, we can study the logistic equation. So that's what we did. But here I have a review, minimal and maximal equilibrium for the evolution problem. Global attractors are studied using sub and super solution by Gomes, Lopes and Gomes, 2005, Rodrigues, Bernal, and Vidal-Lopes, 2008, Ana Prado, I don't read the name here because I have our faces, and Rodrigues Bernal. But anyways, there is a big group in Spain, mostly, that have dedicated a lot of efforts and many, many interesting papers, but I'm sorry if I'm not citing all people that have worked, but these are the closest to what we read and we have done. So they approach the real parabolic problem and try to see how the solution evolves in time to the stationary solution of Alama, Tarantello, and Ollanta. Okay, also the study of stability of positive and negative stationary solutions was faced by Kajikia in 2012, which is a beautiful work with more, let's say, restrictive nonlinearity, but she studied how stable the solutions, the positive and negative solutions are. Which means like if something starts, if you have an initial condition around one of these solutions, the things are going to flow to the positive solution. Okay, when B of X is positive, we have then the works of Gasol and Wet, Sattinger, and also Juliane and I have tackled the problem with an asymptotically linear G, okay? But that's how I learned about how to use the Nehari method for this problem, and then we try to, let's say, apply all our small knowledge to the let's say, to the logistic equation. But it changes a lot. It changes a lot. When B is positive, for example, Gasol and Wet, I'm not going to talk much today, but you have their works, and also they make a lot of comments in our work too. When B is just positive, you have a variational structure. Then a high manifold is of type mountain pass, okay, where you find the ground state. And what they find is, depending on where you have the initial condition, the solution is going to grow indefinitely, it's going to explode in finite time, or it's going to converge to a stationary solution, which means the ground state of the elliptic problem. So Gasol and Wet found 3 possibilities for initial conditions. And they extended some things that had already been found by Sattinger for the ground state. They extended for other critical points. When we started studying the asymptotically linear problem with B of X positive, we saw that the behavior was very different from Gasol and Wet because we didn't find solutions that exploded in finite time. When you have a nonlinearity, which is asymptotically linear, you either have initial conditions that will give you a flow or a solution in time that grows forever, or it gives you a solution or a flow that goes to a stationary solution, which is finite. But there is no situation of blowing up in finite time. So it was fun and maybe unexpected to change so much for the asymptotically linear case. But anyways, this is just a review of the situation when B is positive. Okay, some remarks. The Nehari changes as lambda changes. That's one thing that you find studying this problem using Nehari manifold. Existence and non-existence are linked to the properties of the Nehari manifold, which is interesting and new because for parabolic equations, the evolution, depending on where you have depending on the properties of Nehari, is not well known. It's not known almost at all, okay? Lambda 1, the positive principal eigenvalue. of the Laplacian in the whole space is which determines all the evolutions. This has, okay, with boundary conditions, has a positive principal eigenvalue with an eigenfunction which is positive. And this is our, how can I say, reference. We are always going back to this reference. The positive principal eigenvalue of minus Laplacians in omega 0, where you have a good region where B, no limitations, where B is 0, is also very determinant on how the parabolic equation is going to behave. And of course, if since omega 0 is a subset of omega, which is, we assume, regular, positive measure, everything is good, we have this relation between the first eigenvalue in the whole space and the first eigenvalue in the subset, okay? In the whole set and the subset. Okay, so this is the things we have to keep in mind in order to face the problem using Nehari, the parabolic problem. Okay, adjust the Nehari method, the geometry, for the generate non-positive functions B. And this had to be done because neither Brown and Zhang nor Alaman Tarantello really paid attention to the possibility of B being 0 in a subset and how this would reflect in the whole problem. And even more for the parabolic. Palais-Mayo sequence to find unique positive stationary solutions. We need to prove Palais-Mayo condition, get the Palais-Mayo sequences and see how they converge. Mount and pass on Nehari in order to find the sign changes solution. So what I'm going to explain now is, we find the Nehari set, but for B less than or equal to 0, you have a min for the problem, and then which is positive, a positive stationary solution, and then we perform mount and pass argument on the Nehari manifold, not in the whole space, but over the Nehari manifold. So we're going to see that the Nehari manifold has a min, so it has a ground state, and then we link these two mins and find a mount and pass on the Nehari manifold, which is going to be a sign changing solution for the problem. Nehari method for logistic equation separates the phase space regions of convergence in time. This is a novelty for people that works with the parabolic equations. They don't usually have regions of initial conditions. They start with some kind of, take this kind of initial conditions and see how the problem evolves. Using the Nehari set, we can, in some sense, split the space of initial conditions in behaviors. If you are, take the Nehari set, which is related to the elliptic equation. If you are on this side of the Nehari set or on this other side of the Nehari set, the problem is going to evolve and take an initial condition there this way. And then so in some sense, when we expose our work, let's say the other one and now this one, in groups where you have people that work the parabolic equation, they say, wow, so where you start is going to depend on the profile of the thing at the end, which means at the stationary situation. If you know how to start, you are going to get something at the end, which is new in the way they face the problem. So I think it's interesting for us that working the elliptic equations is to say, okay, if you know well the elliptic equation, you can say something on how to start the parabolic to get to where you want. So this has been interesting. I think Delvino has been working and other people now on parabolic equations, thinking about this too, like initial conditions, taking reference on the Nehari manifold. So let's see how we did. They generate parabolic equation, again, omega is a bound, d of x less than or equal to 0. And of course, if you have just a power here, you want to be in this Sobolev embeddings, which are continuous and everything. So what I'm going to say that we have worked is all just the power problem, okay? And then about the power problem, we have again the words of Young and Tarantello that says, if the B of X has sign, okay, then for every lambda there exists a unique positive stationary solution. If the B of X has some degenerate region, it depends on where you are. So if you are below lambda 1, there exists a unique positive stationary solution. And if you are above, you have no positive solutions for this problem. So this is a summary of, they say a lot more, okay, but a summary that we needed in order to understand where to range with lambda in order to get our solutions. Okay, but this is just for the elliptic equation, okay, not for the parabolic. Here we are talking about the stationary problem, which means we are studying existence of positive solutions for the elliptic equation. All these words, okay. In our case, we consider, since we are going to use variational methods in Nehari, we consider the functional associated to the equation, to the elliptic equation, and Young did it work like this because he worked with sub and super solutions and also bifurcation. But Alama Tarantello define a functional and they exploit mountain paths and linking structures, okay? In our case, we are going to use Nehari, so we define an associated functional to the elliptic problem, which is this, the norm minus lambda and minus the power part. And critical points, as we all know, are the critical points of associated to this functional are weak solutions for our problem. So if you think of all this part as an effort U, we would have basically this I prime of U V. For every V, 0 gives a weak solution for the problem. So in order to study the stationary problem, which is, well, in order to find stationary solutions to which the evolution problem can converge, you have to solve the elliptic equation. And then we solve using Nehari constraint. So the Nehari manifold, as you also know, is the subset of H01 where candidates for a critical point live. So if you take I prime of U times U, okay, these are going to be candidates to satisfy the solution I prime of U times all V. At least for V equals to U, you have to have this 0. So if you want to find a critical point, you have to think about being constrained to M. That's the world where we, let's say, have a chance to find a solution. So we define the set of points that satisfy this equal to 0. I'm repeating because I think all people in the group probably have worked with Nehari too. And because we're thinking about initial conditions later for the parabolic problem, for us, it's not only interesting to know what the Nehari manifold is, but what is outside the Nehari manifold. Because depending on where you are going to start later, outside the Nehari manifold, you are going to see how the thing evolves in time. So we define N plus when the JU0 that defines N is positive and is negative. So these are complementary sets to Nehari. Nehari plus and Nehari minus, okay? So these are going to be interesting when you study the parabolic initial conditions. Okay. The points in Nehari manifolds, as you know, correspond to stationary points of the fiber in F. We call, you take a fiber in the direction of TU and see how this thing has a 0. So it's natural to divide N into subsets corresponding to local maxima, minima, and inflection points. So that's the interesting approach of Brown and Zhang. what did they do? Okay, they decided to approach the how can I say, the elliptic problem using a Hari. But they went further study. Even if you are on a Hari, the points can be local max, local mean, or inflection points. So this is going to be important too in our approach. So we take S plus, S minus, and S zero, which are subsets of N. When you do the fiber, it's a maximum, a mean, or just an inflection point, okay? So the first results of Brown and Zhang that we had to re-study because they didn't have a region where of the degeneracy, let's see when B is identically zero, was this. Suppose you are in a range of lambdas for the logistic problem, but in this case, for the elliptic equation, just the elliptic, because we're thinking about stationary condition. Okay, if you are in the range of lambdas between the first eigenvalue in the whole subset, omega, and the first eigenvalue in the subset where B is zero, then we were able to prove, following basically the ideas in Brown and Zhang, that the S0, which are the inflection points for the Nehari, is just the zero. Then you have S minus. S minus is when you have a local maxima, which in general gives us the mountain pass solution. The mountain pass solution is usually, it is over S minus. But in our case, when you think about B zero or negative, we're able to prove that the negative Nehari is empty. So you only have the possibility on projecting on Nehari by minimizing in the fiber. So this is a consequence of being with a lambda between lambda 1 and lambda 1 omega 0, and also of having B0 identically 0 in a subset. Okay, but this is, we follow the ideas of Brown and Zhang, and it's interesting. You use just functional analysis, and that's what we were able to do. Okay, the ground state solution. So before going to the problem, the evolution problem, we had to study, of course, the elliptic. So we were able to say, if you are with lambda in this range of lambdas, then the functional associated to the elliptic equation is bounded from below, and there exists a minimizer, positive minimizer, such that I of phi is D plus. Additionally, phi is an isolated point, critical point, from other stationary solutions with respect to H01 topology. Okay, I don't see this very well, but anyways. So this is the where we start, let's say, identifying what's going on in the elliptic problem. We find a minimum. This minima is going to be negative because the function is going to go down and up. And we can prove that it's going to be unique. The positive is unique if you have a power. Okay. So taking this into account, we started studying the parabolic equation, some existence in time, global existence in time. So the first thing we want to know is that if you are taking a solution for the parabolic problem, is this going to blow up in finite time, or the solution starting in any initial condition, which is in 0, 1, is going to exist forever? So we were able to prove the existence in global time, which means you start in an initial condition and you are always going to see U. So U is not going to explode in finite time, for example, in the L2 norm or in L infinity norm. In particular, the set of finite time blow-up solution is 0, of course, if they all work in infinite, they exist in for all time. And also, this is very classical if you differentiate the functional with respect to, because U is a function of T and X. If you differentiate with respect to T, this gives this expression which is negative, which means it's classical. No matter where you start, the energy is going to decrease as time passes, okay? And this is also very important in order to study this process. Okay, so this is the first step you do when you try to study the parabolic equation. So I have been learning a lot from this. There are some estimates in order to prove global existence. You have to have uniform estimates. We wrote this down with some details in our article, but this is in some sense just follow the recipe in order to prove that you have uniform bounds, therefore the solution exists in all time. Okay, this is the summary of what we proved in this sense. Let lambda be between lambda 1 and lambda 1 omega 0, then the solution is for all time. Additionally, no solution blows up in finite time. Okay. I'm not going to go into details, but of course, we need to be in a range of lambdas in order to get the uniform bounds, and this is what we do. I want to go on because the part that concerns me mostly is the mountain pass on the Mehari, and that's where I want to. Okay. Since we are in a situation, because of the B, that we have only the zero piece of the Mehari, zero is always, in our case, we didn't exclude the zero. So zero is in the Mehari because J of zero is zero. And we don't have the maximum. We have just a min, so we have S minus. In order to study S minus, we need to know how to project any function that you take in S plus. Not all functions project, but just looking at the functions that project, we are able to minimize and find a critical point, which is a mean in this problem, okay? So we define the B set of functions in the H10, for example, which have norm 1, and the linear part, which is this, and the nonlinear part are less than 0. If you take this, not all functions in H10 satisfy this, but if you live here, you are able to project in S plus, okay? There exists alpha bar such that you are able to project in S plus. And in this case, we are able to prove not just because of the power, okay? If you are not with the power, for example, if you are in an asymptotically linear problem, this is not true. But here it's if and only if because we are in a power. So because our nonlinearity is this power, subcritical power, we were able to prove that the ones that project have to live here, okay? So this is good because then we know how to start and how to project on the Mehari and then minimize on this set of points. Okay. Another thing that we were able to prove was, okay, but this is also known in this kind of power problems. If you are between lambda 1 and lambda 1 omega 0, giving a negative point here, okay, then the solution evolves, or the solution of the parabolic evolves to phi, where phi is the unique positive stationary solution for the problem. So this means that non-negative initial data always evolve, or if they are indeed, always evolve to the stationary solution, okay, to the unique positive stationary solution. So the unique positive stationary solution was found by Young, Arlama Tarantello, and everything. So it's known where they are. And now this is like a strong result because no matter how big your initial condition is, just if it has a sign, it's going to evolve to the min, okay? But then we started thinking, what about we can find, we have a min which is isolated critical point. It is a positive solution. It is unique. Can we find other critical points for the elliptic equation? So we decided to face this using mountain pass arguments on the Nehari manifold. So what we did was, since the I has a min in D, we put everything up, and then we could see the min here, and minus phi is also a min because there is some symmetry, let's say, of the power, because it's a power problem. So phi and minus phi are two solutions. If you go up with them, they are the mean, so you are in 0, 0. And then we started looking if we could do a mountain pass argument from one to the other. Okay, in order to prove the mountain pass argument, we had to prove the geometry on the Nehari manifold, and also Falaise-Mayo condition on the Nehari manifold. Okay, but once we did this, and this was possible to do, because the Nehari manifold is a natural constraint. So everything is easier because Falaise-Mayo condition on the Nehari manifold is going to give the Falaise-Mayo condition all over. So that's how we did. So we defined this, which was our functional translated A. We defined the minimax possibility for a critical point, and we connected one phi to the other minus phi, which was, we connected 0 to 0 going up. Because both are isolated, we were able to prove that both are isolated. So in order to, and isolated min. So in order to leave this phi, you have to go up. In order to arrive here, you have to go down. So you have the geometry of the mountain pass. So that's what we did. And of course, we ended up finding a solution using mountain pass arguments in a level which is above D minus, because the 0 is isolated. So that's how we found this solution. So we call this solution, we call it U star, the mountain pass on Nehari. Note that the solution found may be trivial. Why it may be trivial? Because the 0 solution is up here, because the phi and minus phi are in a negative level. So it could be 0 solution, okay? But the 0 solution already exists, so we try to see if we could avoid it. So if we could find at least sufficient conditions in order to obtain a non-trivial minimax solution. And the condition was this. Consider that you have the first eigenvalue, of course, less than the second eigenvalue. This is true because it's the Dirichlet problem, eigenvalue problem. And the lambda 2 omega by hypothesis, by assumption, is below the first eigenvalue of omega 0, which means, for example, if omega 0 is a very small set, in good region is where everything grows and survives, is a small set, of course, you're going to have something like this, and then you have a range where to work. So assuming a little bit more, assuming this, there exists a mountain pass solution U star of the stationary problem, which is sign changing, and we were able to prove that the level set C is strictly less than 0 in this case. So in order to prove that it's strictly less than 0, the C mountain pass level, we had to use the eigenfunctions phi1, phi2, and phi1, 0. This way, using these 3 eigenfunctions, we were able to construct a path from phi to minus phi, avoiding 0. So what we do is, like, we come out of phi, which is a strict minimum. We stop before 0. We go around, always on the Nehari set, and then we go down. This is a path that connects one and another, so it's in the set of minimax paths, and it avoids zero, so of course the level minimax has to be below. I'm not going to show the calculations. This takes some calculations, and of course we use the eigenfunctions, therefore we have to use these inequalities here. But that's the way to construct the mountain path solution below zero, which means that it's not the zero solution. And then, of course, it's not the zero solution, but it could have zero regions, this U star. So we are able to prove that U star changes sign. Why does it change sign? Because the positive and the negative are unique in this case. So of course, this U star could change sign, but it could have regions where it's also zero, but then you use Hopf lemma and these inequalities in order to prove, no, this function has to cross, every time it changes sign, it has to cross the transversally, okay? So these arguments using Hopf lemma, maximum principle. Moreover, U star has a Morse index, at least one, because it is over Nehari, it's a mountain test found on the Nehari set. And because of this, we are going to show that, of course, it's an unstable solution for the parabolic equation, okay? Okay, I put a picture here that's, at some point, I realized that what we had was a Nehari set like this. This is the beam. It's a sculpture, which I like very much. I have been to this place. It's in Chicago. This sculpture, I don't remember now too bad that I didn't look the name of this sculpture, but he's very famous. And basically, at least in my mind, what I get about the Nehari set is a picture of a beam like this, okay? Here I have phi, here I have minus phi. This is the zero level, so the solution U equal to zero lies here on the top. Why does it lie here in the top? Because all the levels, here I'm looking at the levels of the energy of the action level, and all the action level are negative. The most negative it can get is in the minimum point, which I call D bar. Here is D bar, and in my mind, what I'm finding is a mountain pass over this beam, okay? So U star should be around here. Of course, in order to avoid the U star to come up to zero and go down, I had to let's say, take the assumptions of lambda 1, lambda 2, and lambda 1, 0. 3 eigenvalues. In fact, Juliana and I were able to prove for some domains, for example, domains which are convex, in the omega 0 domain, also a ball inside a convex set, we are able to prove that we can do this construction avoiding the second eigenvalue, just for lambda between the first eigenvalue and the other eigenvalue. But then we got into this setting, this environment of studying the dependence of the eigenvalues with respect to domains, and continuity of eigenvalues with respect to domains. And that was nice because we studied and we learned a lot, but I discovered another world of problems, which is the world where people study the continuity of eigenvalues with respect to domains. Mm-hmm. And it's a different world. So for very restrictive domains, we are able to avoid the second eigenvalue, to do our construction up, around, and down. But then we didn't go into this, maybe in the future exploit a little bit. But in my mind, that's what I have, okay? Maybe if the beam was coming zero and down, then you had to pass through zero, and the solution would be zero. So in order to have a solution which doesn't go to zero, doesn't pass on zero, we had to have this lambda 1, lambda 2, and lambda 1, 0, okay? But anyway, so now we have a picture of solutions for this problem, stationary solutions. And we want to know where to start in order to go to the positive solution or to the just found mountain pass solution on the Nehari. So that's where we had to use Nehari plus and Nehari minus. If you start outside Nehari, but with J positive, what's going to happen? If you start outside Nehari with J negative, what's going to happen? So we were able to see that not all, but at least there exists initial data outside Nehari on one side and in the other, which flow to our found mountain pass solution. Okay. For us, this is very interesting. Juliana has been to more parabolic groups exposing this, and they say, wow, but what does it mean in ecology to have this negative positive solution or a solution that changes sign? Because they are always thinking about population, and the population in the domain should be the number of population would be in the positive number. So they were saying, why are you studying the problem that changes sign if it doesn't mean anything to us in ecology? I have, at least my intuition is, if you find a sign changing solution, what you are finding is like two populations living in the same environment and how they could be distributed and how the evolution problem would come to them, which means like if you start with the initial condition, if this evolves to a sign changing solution, this solution or these initial conditions here would evolve to two species surviving in the same domain. That's my intuition. But anyways, I don't know much on the application. Because this was questioned to Juliana and she said, yes, in fact, if a population is negative, what does it mean? In my sense, although I don't know much about ecology, anything, is like you have two populations surviving at the end of the thing. When they stationary, they are like this population one, population two, and the good environment where they survive. Anyways, but in terms of mathematics, it was fun to study this and see how the problem can evolve if you start in n plus and n minus. So I'm going to show to you, just to finish, how we study this problem. Okay. What you do, or what we do, is we linearize the problem around U star, the mountain pass solution, okay? We linearize the operator, the elliptic operator around this, and we see the eigenfunctions of the linearized operator. Let me skip to the next. Okay, the linearized operator is this one, okay, around U star. Take this linear operator. Now it contains the derivative of f of U star times U, okay? This is self-adjoint in L2 with domain in L1 and H10 and H2, and the spectrum is entirely composed of eigenvalues. So this is a very good operator. Let's call Mi the non-decreasing sequence of eigenvalues, repeating according to their multiplicities. And the psi I is the associated eigenfunctions, okay? Since it's a self-adjoint operator, you have this sequence of eigenvalues. They're going to go to plus infinity, and there is one negative y because of the mountain pass structure of U star. So at least one, we don't know if we have more, but at least one, I think because of the structure of S plus, it's just one negative eigenvalue, but at least one negative eigenvalue we have. If you have a negative eigenvalue and you write down L2 in terms of these eigenfunctions and try to work the parabolic problem, you end up with functions which are exponential to the eigenvalues minus eigenvalues t times eigenfunctions psi. This is a sum which gives a solution of the parabolic problem. And a solution of the elliptic problem is going to be a sum of these eigenvalues, because it's just the problem in L2 omega, okay? So if you split L2 in terms of these eigenfunctions and these eigenvalues, the solution U star that we are working with can be written this way. So we separated a psi 1, okay, because has the first eigenvalue, which is negative, and then we started writing from 2 to Q. Why Q? Q is the maximum negative eigenvalues you have for this problem. Since the problem is in a self-adjoint linear operator, the eigenvalues are going to go to plus infinity, and they are discrete. So just a finite number of them are negative, and we call the number, let's say, if it has 10 negative eigenvalues, we call Q10. So we write U star in terms of the first eigenvalue from 2 to 10, and all the eigenfunctions after 10, which is from 11 to plus infinity, are associated to positive eigenvalues. Okay, why this separation is important? Because the functions which are associated to negative eigenvalues in the parabolic description separating variables in terms of exponential to the minus mu t times psi I, for example, mu I t psi I, minus with minus is plus, which means that if you start an evolution problem there, the thing is going to send you away from the point. So this is like an unstable direction. But if you start with a positive eigenvalue, the exponential to minus a positive eigenvalue is going to go to 0, because it's exponential of a minus constant t. As t evolves, this goes to 0, and then you convert to something. So it's important to separate in order to see the stable and unstable manifold around or at U star. So this is the study we have to do in order to see the evolutionary problem around U star. Okay, the thing is, if U star does not have a positive part associated to it, if it has only negative parts, it's because it's a source. Everything that is around goes out, out, out. Nothing comes in. And we were interested to see, if you start with an initial condition very close to U star, if there is something that is going to go there, okay? Because the minimum is an attractor. Everything comes to the minimum because it's a stationary solution which is isolated. So everything around there goes to the minimum. But now we have a mountain pass solution. The question is, what's going on around this solution? If you start very close, even if you start with a positive initial condition, although here, if you start with a positive initial condition, it's going to run to the positive solution. If you start with something here, is it going to run to the mountain pass, or if the mountain pass is the source? Everything goes out. So this is the study you have to do, and it depends on the number of eigenvalues positive and eigenvalues negative. So we have to find something around Q plus 1 to infinity. AJ here has to appear, because if they are all 0, no choice. It's going to be a source. Okay, so that's how we did. We were able to prove using that this U star is in the Nehari part S plus. So being at S plus and being between the lambdas that are good, we were able to prove that for at least one AJ, this thing does not disappear. So this projection here, for some I, is different from 0, which means you have one term at least here in this decomposition of U. And then, okay, this is what we use, the linear problem around linearize around U0, our equation. And then what we find is this. If you take X1, the finite dimensional subspace of H0, the finite dimensional subspace of H0 is spanned by the eigenfunctions which are associated with negative eigenvalues. And X2, the infinite dimensional subspace is spanned by the eigenfunctions associated to positive eigenvalues. Okay? The local stable manifold, which in the books of parabolic equations is denoted WS log, is tangent to X2 at U star. In addition, there is a neighborhood of 0 in X2, okay, such that you can describe the stable manifold around U star as U star plus eta, which is in this neighborhood, plus something of small order with respect to this. So this is the way in the parabolic literature, they describe under these conditions that we are, everything is smooth, u to the p, u to the nu is a power nonlinearity, so everything is good. The stable manifold is going to be described this way. So what did we do? We proved that for some I, the psi is not, has a term describing U star. So we used initial conditions, which were something like very close to U star, to our mountain pass. In the direction, although it's very close, it's not on the point, it's a little bit further, but in the direction where you have a positive eigenvalue, in the direction of the eigenfunction that has a positive eigenvalue. If you start here, this is going to be in the stable manifold. Therefore, it means that it evolves in the direction of exponential negative t. Goes to 0, therefore you end up here. But how do I know that I am in Nehari plus or in Nehari minus? What we did is, to be U star is a mountain pass, since Nehari is a natural constraint, this is 0, okay, so it's a critical point in the whole space. And then what we did was the Taylor expansion of the Nehari expression, Nehari functional, at U0. So Taylor expansion at U star. So if you take the Taylor expansion of the Nehari function in this point, it's going to be the Taylor, the J expression in U star, but this is 0 because this is on Nehari. And then you have this. But once you have this, we do the calculations and then we end up with the eigenfunction, because you have the second derivative of the function, which means you have the linear operator, the L linear operator here, in fact. So the L linear operator on this function is mu I, epsilon is multiplying, so it comes out because this is going to be linear, and AI appears when you do this on this direction. Anyways, it's just calculations using the expression of J prime, which means I2 prime, okay? So, and then a small order term, we can prove that this is a small order term. Therefore, if you want to know that U0 is on Nehari plus and Nehari minus, it depends on the epsilon here. Suppose AI, for example, without loss of generality, since this is not 0, it's positive, for example, or negative, it doesn't matter. Mu I is positive because it's the first, it's an eigenvalue which is positive. Depending on the sign of epsilon, you have this sign of this J is 0. Therefore, for epsilon, for example, positive, AI positive, this positive, since this is a small order term, if you start very close to the mountain pass solution, you're going to be in Nehari plus. And if you take epsilon negative, you are going to be in Nehari minus. Therefore, the result follows, and we have this theorem. Let me go back here. You have an initial condition in Nehari plus that flows to the mountain pass solution, and you also have one that flows from Nehari minus. So the mountain pass is in fact, let's say it's not a source, it's not a sink. Depending on where you start the evolution problem, it runs to the mountain pass solution, and depending on where you start, for example, in the other directions, negative is positive, the exponential starts growing, and then you are flowing down. So this is the profile of the, let's say, the mountain pass solution with respect to the evolution problem or the parabolic problem. So that's basically the idea. I thank you all for your attention.
Thank you very much, Liliane, for this very, very nice and interesting talk. Is there any question for Liliane? If there is any question,
yes.
please, yeah, go ahead, Victor.
Yes, I have, let's say, two small questions. Well, first of all, thank you for your very nice talk. And my first question is, do you have, or maybe it is just implicit, a rate of convergence towards the any initial atom to the stationary state? Is it exponential? Is it it polynomially converge? How fast is this convergence towards
From the little I know about the parabolic, it's exponential in time.
All right.
It's exponential in time.
Okay.
Because
And
you end up having the evolution U2, UTX is the evolution, okay, problem. It's like the semi-flow. So this is going to be a sum of exponential minus lambda I(t) times the eigenfunctions times a constant. So it's like a sum of this kind of things.
All right. Okay. Thank you. And my second question is just also a curiosity, is does it make sense to change in your problem, and how does the analysis change if you put Neumann boundary conditions instead of Dirichlet?
There is a sense in ecology on this, and I think there are many people working on this nonlinear boundary conditions and also Neumann boundary conditions. After the solution of Young, we didn't follow because we were interested in the elliptic problem with Dirichlet boundary conditions. But there are many citations that use the Young's idea to approach the problem with Neumann boundary, which in ecology, they say it's very nice problem because it's like the population cannot go out of the boundary.
Yes.
They can get close, but they cannot flow out or leave the boundary. So there are many works that give citation of Alama, Tarantino, and Young in the Neumann boundary conditions. And I think nowadays would be very interesting to study non-linear boundary conditions for this problem. Maybe even using this kind of approach that we are using, Nehari associated and everything. Because usually the people in parabolic and also late as Young, they used sub and super solution and all these other methods.
All right.
So I think there are problems.
Thank you. I have also a question. You're interested in finding sign-changing solutions. And by the way, I like very much your interpretation of sign-changing solutions. I also think there is something to it, like in separation phase of two populations. I like it. My question is, if you're interested in sign-changing solutions, another way of trying to find one would be to use the Nehari manifold. So positive and negative part in the Nehari manifold, and you minimize in that set. Did you try that, or why did you go for the mountain pass approach and not the Nehari approach for, let's say, the sign-changing Nehari manifold?
The sign-changing Nehari. Yeah. We didn't go because we knew that if we could find another solution, it would change sign because we had uniqueness of positive solution. Yes. So since you have, in a case you don't have uniqueness, this would be interesting.
But I mean, let's say that you have a unique positive solution, and now you minimize in the sign-changing Nehari, meaning the subset of the Nehari where the elements have non-trivial positive and negative parts. This is like
Okay.
the subset of the Nehari. Usually, if you minimize here, you also find a sign changing solution.
Yes, we tried a lot. I think this would be a very, very interesting thing to find, is minimizing on sign changing Nehari functions. If you minimize on sign changing Neharis, you immediately get that you are not obtaining the zero solution. We tried this a lot, we could not. That's why we ended up using the first, second eigenvalues, constructing a path, going from one to another. But for a while we tried, we didn't succeed, okay? But if you can succeed, this would be a very interesting thing to find out if the one we found in the mountain pass sign changing solution is the minimum on all sign changing Nehari candidates.
Which is the least energy time changing solution by
Because
construction.
then you get, of course, that this is not going to be a zero solution. And you are not constrained to the eigenvalue lambda 1, lambda 2. We tried this a lot, but we didn't.
I think this is a very interesting, probably very hard problem, in particular because there is also this other paper saying that depending on the domain, the nodal sign changing solution, the least energy nodal sign changing solution, and the mountain pass sign changing solution can be different.
Yeah.
Exactly. You know this result. Okay.
So that's when we realized, okay, forget the minimum on all the change sign, because it depends a lot on the set omega.
True, but on the other hand, if it's different, then it has more syntax zero and probably it's more stable. So maybe you don't have to have these problems of if you need to cook two special initial conditions to go there, but maybe it's more general, no?
Yeah. In fact, we tried, so we didn't succeed. We started seeing, okay, let's use the eigenvalues, and then we were able to construct a path. But just to construct a path, we have to do a lot of calculations. That's where we are. But at least we were able to calculate the path.
Okay. No, I really like your seminar very much. And you mentioned quickly at some point that this has also been explored for other operators. Were you meaning like fractional Laplacians or something like this?
Yes.
Or, okay.
I have seen, for example, in my department, there are specialists in parabolic and logistic equation. William Sintra, for example, he came from the north of Brazil, I think from Fortaleza, maybe, and he has been working with this Spanish group of this logistic equation for years. And I have seen some of his works recently on different operators, like non-local operators. But what do? Sub and super solutions again.
Okay. I see.
So
Okay.
they don't know about, or very
Nehari, and there is a window of opportunity then.
The Nehari argument. So maybe putting together Nehari, you can get another result.
And one last question. At the beginning of your talk, you mentioned these three cases where you could have a discontinuous solution and something that bounds these two regions, but only for strict inequalities. So I was wondering what happens in the boundary case when lambda is equal this sigma 1 or this sigma 2 in the pictures that you mentioned.
There are results for existence of 1, 2 positive solutions. For example, if D changes sign, Alama Tarantello, they treat the boundary cases.
Okay.
Or Young. So people after, what happens in the boundary case is like the solution has singularities in zero, has singularities in the domain. So the solutions are like, they are not C functions, good functions.
I see.
As you get to, for example, if you take lambda and start getting closer and closer to the lambda 1 omega 0, the solution starts getting up and up and up. L infinity norms are growing. So there is kind of an explosion in the L infinity norm. I don't know how they would draw this, but they treat these cases too.
Okay, well, thank you very much again, Liliane. Is there any other question? If not, then let's thank Liliane again. Thank you very much.
Thank you.